Yes, so from today we will be continuing the uh, heap and priority queue problem from the NeetCode, and today we are going to solve the problem for this task scheduler, problem number 621. Okay, so let's first read through the problem, then we will watch the solution because I tried to solve it by myself. I am not able to understand currently like how to solve this problem. So we are going to watch this video and then we'll try to solve the problem. Okay, so let's first go through the problem. Okay. So task scheduler, okay. You are given an array of GPU's tasks, each labeled with and later from A to Z, okay, and number n. So basically, there are there are tasks from A to Z given as a array, and then a number n. Each GPU interval can be idle or allow the completion of the task. Okay, so each time the GPU runs, it can either be idle, the EP cycle, and or it can complete one task. The task can be completed in any order. Okay, so but there is a constraint. There has to be a GPU of at least an interval between two tasks with the same level. Okay, so simply basically if there is A, we cannot run the A task again until two another two interval has passed. So first it's A, then B, then C. The two interval has passed, so then again we can use A. Otherwise we cannot run two similar tasks one after another. We need to wait at least n intervals. So that's simply that's basically the problem. So let's go through the solution video and try to understand it.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem task scheduler. One of you suggested this problem, and I think it's a pretty good one. So we're given an array of tasks. It's a character array, and it's going to be limited to the characters from uppercase A to uppercase Z, so 26 characters. Each of the characters represents a task, and the task is something that the CPU needs to process. And the tasks could be processed in any order. Each task takes exactly 1 unit of time to process, so that's good because it makes things simple for us. And for each unit of time, the CPU could either process an entire task or it could be idle. And the reason it would be idle is because we're also given non-negative integer input n that represents the cooldown period between the two same tasks. And the same task is represented by the same letter, the same character in the array. And to understand this, let's take a look at an example. And by the way, what we actually want to return is the minimum number of units of time that the CPU will take to finish all of the tasks. Let's take a look at this example. We're given these tasks, right? 3 A tasks and 3 B tasks, and the idle time we're given is 2 units of time. So basically, let's say we processed an A task, right? That takes us 1 unit of time to process. Now we process a B task. And now we know that before we process another A task, we have to wait 2 units of time. So, let's say we process an A. We can't process another A. We have to wait 2 units of time before we can process another A. So what are we going to do in the meantime? Well, there's a B as well. So let's process one of the B's. And now for this B, we know we actually have to wait 2 units of time before we can process another B. So the next time we can process another B will be at this point in time after we have processed our second A. So now the question is, can we fill this spot with anything, or are we going to have to be idle at this point in time? And there aren't any other characters, right? We had 1 A and 1 B. Now we have 2 A's and 2 B's remaining, so we can't do anything. This has to be idle. We process an A, a second A, and a second B. That means that before we can process another A is going to be 2 units of time. So this B, and then another unit of time, and then another A. And we also processed a B. The next time we can process a B will be at this this point in time. So at this point, again, we are going to have to be idle. But the good thing is that this is the entire, like all the tasks we were looking for, 3 A's and 3 B's. So as you can see, it took us 1, 2, 3, 4, 5, 6, 7, 8 units of time to do this. So our output is going to be 8. So now let's think about a general approach that we could come up with to solve this problem. So let's say we had this as our input. First thing to notice is we're going to be given characters A through Z. It doesn't really make sense to worry about which character we're looking at, right? There's really not a big difference between a B and a C, but we should keep track of how many of each character there is. So we know there's 3 A's, 2 B's, and 2 C's, right? We don't even have to worry about the characters anymore. We can just focus on the numbers. We know that there's 3 of one character, there's 2 of a different character, and then 2 of another character. We know that the idle time in this case is 1. What order should we process the characters in? It's probably better to process the more frequent character first, the more frequent task first, because we know there's going to be some idle time, and processing the more frequent one first basically gives us more time to not be idle. And I'll show you the intuition behind that. Let's say we did a C first, right? We do C, we know that the idle time is just 1, right? So then let's say we do B, and we're allowed to do another C right away. Let's say we do that, right? We do another C, and then we do another B because the idle time is only 1, right? So now we've already processed all the C's and the B's, and all we're left with is 3 A's. Okay, let's process one of the A's. Okay, great. But now we have an idle time. We have no other characters available for us, so we have to wait. And then we can process another A, and then we wait, and then process another A. So in this case, this was one way, but did this minimize the total time that it took us to process all the tasks? A different way would have been to start with the most frequent character, right, A, and now there's only 2 A's left. So now what's the most frequent? Well, you could say A again, but we know that there is an idle time of at least 1. So at this point in time, A is not available to us. So we have to process a different character, let's say a B. Then A is actually going to be available for us again. So we could process the A, or we could process the C. In this case, it doesn't really make any difference because there's 2 of each of these. So we could do either one. Let's just do C. So then there will be 2 A's, 1 B, and 1 C. Then we'll, of course, want to do the more frequent character, the A. And then there's going to be 1 A remaining. We can't process another A without at least 1 unit of idle time. So let's do B, and then do C, and then we can do A, right? This also is a valid way, and this one actually minimizes the idle time rather than this one. And what is the idle time in this case? It's about, not the idle time, the total time in this case is about 7 as opposed to 9 in the other case. So that's kind of the intuition why we're going to try to do the more frequent task first and then the less frequent task. How we're going to be doing this is by using a data structure called a max heap, which will allow us to continuously figure out which task is the most frequent one. And the max heap can actually allow us to determine that in log n time, right? If we have a bunch of these, we could figure out which is the most frequent in log n time, which is good. But in this case, actually, it's even better than that. It's about log 26, since we only have 26 different characters. This is kind of a constant time operation anyway. But I will say that the overall time complexity is still going to be big O of n. One, because we are going to have to, count the occurrences of each task. So we're going to have to go through the entire input. And we're going to be, popping every value from our max heap and adding every value to our max heap. So the time complexity is going to be big O of n. That's also going to be the memory complexity. But now to the actual algorithm itself. We're actually going to use one other data structure, a queue. It's not required, but I think it makes the problem a little bit more organized. So let's start off with the max heap, right? We have 3 integers. We're going to be adding integers to our max heap, not the characters. We're going to be taking the counts of each task and adding that to the max heap. So we're going to have a 3 and a 2 and another 2. And by the way, when I actually code this up in Python, we don't have a native max heap. So the way we only have a min heap. So the way I get around that is basically by taking each of these values and making it negative. In a max heap, we want to pop the maximum, and we can do that in log n time. So in this case, we'd pop the 3, which is the maximum. But in Python, we're actually going to do it the opposite way. All of these are going to be negative. So we're going to end up popping the minimum, which is going to be -3. But we're going to, assume that it's a +3. But yeah, so that's the idea. First, we're going to pop the 3 or the -3. You can think about it however you want. That's the most frequent. But now we want to change the count from being a 3 to now being a 2, right? Because we just processed one of the tasks. So, if you have a negative, you'll have to add 1. If you have a positive, you can decrement it to 1. In my case, when I write the code, I'm going to be adding 1 to this. But now we're actually going to be taking this and adding it to our queue data structure because we know that there's some amount of idle time for this task. At the current point in time, initially we were at time equals 0, but we just processed the task. So now we're at time equals 1. And we're going to add this integer 2 or -2 to our queue. But we're also going to be adding another value to the queue. And that's at what time is this task going to be available for us to process once again? Basically, at what point can we take this and add it back to our max heap, right? What's the idle time that is going to be remaining? Well, right now we're at time equals 1, and our idle time for each task is n equals 1. So basically, we're going to take n and add it to our current time. So it's going to be 2. Basically, at time equals 2, this task is going to be available for us to add to the heap again. So that's what the second value. This task is going to be available time. So it's going to be 2. Basically, at time equals 2, this task is going to be available for us to add to the heap again. So that's what the second value in this case means. And once again, we're going to pop from our max heap. We're going to pop the -2. And that means we have processed the task. So now our time is actually going to be time equals 2. We're going to take that task. It was a -2. We're going to add 1 to it, which is going to make it a -1. So then we're going to take that -1 and add it to our queue. And at what time is that task going to be available to add back to our max heap? Well, it's going to be 2 plus 1 because n is 1 in our case. So at time equals 3, this task can be added back to our max heap. But now that we're at time equals 2, we see that this task actually is available now to add back to our heap. So let's pop it from our queue and take the -2 and add it back to our max heap. And at this point, you're probably starting to get the idea. So I'll just kind of fast forward through this. We're going to pop this again, set our time now equal to 3. We're going to take that -2 heap. And at this point, you're probably our queue and take the -2 and add it back to our max heap. And at this point, you're probably starting to get the idea. So I'll just kind of fast forward through this. We're going to pop this again, set our time now equal to 3. We're going to take that -2, add 1 to it. So it'll be a -1. We'll add that to our heap. At time equals 4, it's going to be available for us to add back to the heap. This value can be popped from our queue. We can add a -1 here. And then start the cycle over. So let's pop this value over here, add it to our queue. We're running out of space, so let's add a little bit more space. That -2 will become a -1. The time now will actually be 4. So the time that this can be popped is going to be at time 5. We see it's time 4, so this can now be popped. So we add that back to our heap. -1. And now it's time equals 4. So I'm really going to fast forward through this. It'll take 1 more unit of time to process this task. But now this task, as you can see, we're going to pop it. It's a -1. We're going to add 1 to it. So now it's going to be 0, right? 0, once a task becomes 0, we know that we don't have to process it anymore, right? So when it's 0, we're not going to add it to our queue because it doesn't have to be idle. It's never going to be added back to the max heap. Once it's 0, we're not going to do anything with it. So, we pop it from our max heap and there's nothing left. But we see that this value over here, right now it's going to be time equals 5 actually. So time is 5. This can be added back to our max heap. Let's add that -1. Sorry if it's getting a little bit messy. But next we're going to pop this from our max heap. It's going to become 0. So we don't add it to our queue. Now it's going to be time equals 6 after we process that task. And lastly, we have 1 task remaining. We pop it, we process it, it becomes 0. We don't add it to the queue. So now after processing that task, our time is 7. So we can return 7 in this case. And that's pretty much the entire algorithm. So that's what I'm going to be following. Even though popping and pushing to a max heap is usually a log n operation, in this case, it's really going to be a log 26 operation. So the overall time complexity in this case is really just big O of n because we have to just go through every single task. Okay, now let's write the code. Okay, so now
What we're going to do is let's just add a hash map to count how many times each number exists, so that we will create a max heap. So how can we create
Let's code it up, and you can see I have a couple of comments just to kind of help simplify things for us. And I usually don't do this, but we want to count the occurrences of each character in the input. It's a list of strings. We could just run through that, loop through that, and add it to a hash map, but you can actually do that with a built-in way in Python, just using a counter, which is literally a hash map. It'll just do that for us, so we don't have to write the...
So we need to get a hash map. So map of char int this counter. So now for each char c in, that's what we're going to do. Which task from task, what we're going to do is simply count task specific. Once we have counted all the tasks, we need to again go through all the counts and create add it to the vector, so that we can create a heap based on that. So let's first we can add the element directly by counting the second value from the hash map and add it to the heap. Heap. Okay. So practically, so we need max practically. So what will we simply do int. So vector of int, yeah, that is priority queue. Okay. Now what we need to do is we're gonna so what we do is priority queue push. What do you need to push? Int push here. Once we push the pair second, we have created a max heap of all the counts. So now let's create a queue of what do you need? Pair. Okay. Pair of int. Okay. So now let's name queue. Okay. Now what we'll do is we're gonna loop through we're gonna do this until priority queue is empty. Until priority queue until queue is empty, because both is empty. Okay? So if you see this, go back, we keep on adding, but then there could be a situation that there is nothing on this because the time has not passed. Let's say we have to add this in 6 seconds, so we pop this, we go to 6 seconds, so it's empty, but on 6 seconds we need to add it. to have. So on the 6th second, you're gonna add the element to this. This will be like we have 1 and nothing on the next task. So what we will do is simply while either priority queue and queue are both are empty. So while the queue is not empty, or even queue that is not empty, while any of this is not empty, whatever we do is simply so first iteration this will be empty. So whatever we do is tell the top element from the queue. So let's do int top top task order, and that will be simply priority queue dot top, and then we need to pop that top so that we can push whatever the task is -1 to the priority queue again. Okay, so what we'll do is put that pop, then we could push whatever the top task -1. Okay, so once we do this, we push step. So we need another variable, it's time. Okay, int time 0. So every time this will run time plus possible. So we pop it, add it. We do not add it to this. Once we pop it, we add it to the priority queue. So we add it to queue. So queue dot push. What do you need to push? You need to push whatever the top element and whatever our time plus n. So post pop the first task, increase the time, pop the first task, take the first task, pop it, then we'll have another task, we add this to this. Okay. So before even doing this, what we need to do is check if queue is not empty. So what we're going to do is we're going to check if queue dot front, if queue dot front, if it is not empty, what will check if it is not empty. And queue dot top value second value equal time. Okay, if it is equal to time, it is not empty, and if top value second value is equal to time, what we will do is we're going to add that top value to the end of the, and add that top value to the priority queue. Okay, So pq dot push p dot top dot first element. Not until 10. So first, the first iteration, it is empty, so this is going to run. We're going to come here, we're going to pop the first element, and we're going to add one, whatever the top element -1 and plus time to the this. And in the second iteration, still we have added the element to the queue, and this is still not empty. Right? So whatever the second iteration, the time is equal to 2 at the 2 second. We check, can we add? Okay, so for in first iteration 1 plus 2 at 3 seconds we will be able to add. So this is this will not be true. We will come here. Whatever the second iteration is, that this is this one. Okay. So this will be this one. So this will be this one, and second iteration will add. We'll come to the 2. We'll add b. So our this will be empty, but this isn't empty. So we need to be idle. Okay. So if we come here, if we try to get the top, it will give an error because the top element, because it's empty. So simply the error is if pq dot t is not empty. Okay, if it is not empty, then only we do this. Okay. So in second iteration, once we add b, we'll come back. Priority queue is not empty. We have pushed this both to the that. Then in third iteration 3, so it is not equal to top, so nothing will happen. It is empty, so nothing will happen. Again will come, and then top element, that is a, that is 3, will be there. Time will match, so we'll again push that element to the queue. It will come here. See if it is not empty, we'll pop that element from we'll take that element, pop that element, task minus this will be this. If t is the task, sorry, if top task, top t is the task equal 0. If it is not equal to 0, then only add it. Okay, if it is equal to 0, do not add it, everything, because we have completed the task. So, and this will be the return time. Okay. So in third iteration, it is done. Add it. Then again we click on, then on the first iteration, so when we have added 3, then this will match to the 3. So we'll push this. It is not empty. We'll process this. We'll pop it again. Pop it again. We'll get the task. That is, you can see how many times it is. So still, once we pop it, we have 2. So 2 times this one, so we still have 1 time to remaining. Once we pop it, so 1 time we'll add it to this one, then we'll have b. Again, in the next iteration, we have popped the b. We'll have once we do this, once we add this, we need to q dot pop the once we then we have a b. So b added, b will be processed in the next iteration. This is empty, but the top element is currently a. The type does not match, so nothing will happen. This will be empty. We'll log in next iteration. So now and top queued up. Sorry, not top. Front. Second. Front and queue. We have to do the front element. Okay. So first we got it properly. Second iteration, we needed output is 10, we needed 6. So basically what is happening, I think instead of going through the only the top task, so but also we are getting more so why is this wrong answer? Why will be why is this happening? So yeah, I think this while condition is somewhat problem. I think because if this is not empty, this is not empty, so we need increase. We need to push. And let's try this one. Okay. So at first iteration, we need 6. Then first iteration it will come here. Nothing will this will not run. This will run. We'll add a, that is 2 times 2 into the we'll pop it. We'll add the top element. We'll add this to the queue in second iteration, and time will be 1 plus 2 seconds, and second 2 seconds. So in first iteration, we need to add it times before. Otherwise, let's first iteration, like at time one we are doing this. If we add this, so this will be at 0 seconds. So we never process everything at 0 seconds. So this will be 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7. So we'll have to be pointed 2. So we'll have to, that will be 1 plus 1 plus 1 plus 1, that will be 2. It will come here, the time will be 2. So this will match. We'll add it to the priority queue. We'll put the priority queue. Priority queue will arrange it, pop it. Then again there is a task. We process the task. So let's process something. Sorry, I think there is task. So we'll get the top task. This is 1. We pop it. Once we pop it, it is still 1. Instead of doing this over here, we need to do it everywhere. Once we pop it, the top task will be top task minus 1. Task. The first is 2. We pop it to 1. 1 is added. Then in the second iteration, we'll have again 1. We pop it. So the last element will pop it. So you do not need to add it again. Okay? Here there is only one element. We'll pop it. We'll come here. We have popped it, so we do not need anything. We need to push that in. We got these selected. So any task that we have popped, like once we popped it's 2, now there is 1, we add it. There is 0, there is we have completed the task, we do not add it. We just need to add it before. First we need to check if it is not empty. With procedure we add it, push it. Second iteration that time. Now it's working. Okay. The first we need to check the queue. Then we add it to queue. We added it. So in that iteration, whatever the top element of the queue is, in the first iteration nothing is the queue, so nothing will happen. In second iteration we have added element to the queue, but we just added. So this should not be available and the previous element. Okay, so now it's working. Okay. So let's put this problem to the let's give it a ChatGPT. I try to simply let's see if there is any simplified solution for this one. Okay. Just optimize this article. So the issue is this problem. This condition. You only check the one task per time unit and only if the cooldown ends exactly at time. You only check one task per time unit. Only if the cooldown ends exactly at time. Simply I was thinking like we need to go through all the element in the queue. If there is any other element in the queue which can't be popped, we keep on pushing if this is important. Even if there is a second time, and both needed to be added at the exact time. But this will never happen if it is equal to time, even less than or equal to time. Okay. So this will is anytime we'll get to that time. So that will take 1 second. We added it, so this will be n+1. If it is 0, this n is 0, so we can add this the time. So at exact time we pushed it, we'll pop it, we'll add it to the there is also a mathematical formula solution. Okay. So max frequency, highest frequency, and max count number of tasks with the frequency. Max frequency minus 1 into n+1 plus max count. Final answer is max total task. I can walk you through the try it and compare this one reference to statement. Simply we need to do this. Nice answer. And we need to just put down. I don't think this will like do anything else. Because we are pushing it to the back. Even this is the solution. Okay. That's if you want to go to the driver, second expression. This talks like prepare full reflection of accuracy. And then the formula was very common in interviews. It about the simulation and it is faster reason but practicing the pattern. E plus greedy. Just step introduction. This program understand the pattern related page of it's 3-3. So next step is 3-3. So start with simulation. So grab time, PQ, and keep don't read. So formula approach. This is the normal approach. The one we did it with the estimation approach. And let's go to the formula approach. So 3 where max count of 2 as A and B both of max frequency of 2. So what do you do is build a structure A space B space A. Okay. Because you have 2. So the max frequency is equal to minus 1 is equal to 2 gaps. So 2 gaps. So each gap has been must have size of n is equal to 2. Yeah. Now fill the task B. If the D we need time equal to max function is 1 into n plus 1 plus max count. So plug in that value. The answer from this 8. So total task is 8. So max of 6 and 8. 1, 2, 3, 4, 5, 6, 7. 8. Why this much? Okay, put inside our simulation gives 7, but formula gives 8 because the formula assumes the perfect spacing, but we had enough task to feel ideal slot better duration during simulation. So this is equal to max of task size and max function. So but let's see what I can compare this guy is 7, so you can say 7. Compare compress this case to 7. So let's give code. Okay. Publish a project. Solution suppose from 26. We added T minus A capital A. So now the max frequency is getting what with the moment that is frequently protocol. What with the max constant is 0. So let's add for the frequency. Max frequency. Add from max frequency. All we need to max frequency, we get the max count. Once you get the max count, we do part count that is max frequency minus 1 and part count and plus 1. So that's all it is. Into part count into part length plus max count. And get the max count is 0, right? You get the max frequency. If any of the keep on increasing. Increase the max count by 1. So there is 2, 3. So this will run twice. So we'll have 2. So max frequency minus 1. So 3 minus 1, that will be 2. And then m plus 1, that is 2 plus 1. So that is 3. And this is 2. So 2 plus 3, that is 6. Plus 1 plus max count, that is 2. So 6 plus 2, that is 8. So whatever the task dot size task dot size that in task dot size comma result if our task dot size is what is set. So basically what we're doing is we're creating a vector of a size so that we can count the elements of it. So vector of int, okay, where is it? Okay. Frequency, let's make it of size 26, 27, 26, because a minus a will be 0. Okay, so for each char it's a task int is the tasks what we want to simply at that position, that is frequency whatever our TS task is minus whatever our a gives, we can do is count it. Okay, that iteration we can count it using heap. Okay, also let's do that. So now once I have count, we're gonna use the get the maximum in this frequency. Okay, so int frequency limit. What is the max frequency? That will be star max element will be instead it's begin. Okay, it's begin panel instead. So once we'll have a max frequency of the element, we need we need how many times that max frequency occurs. So for that we'll have an int max count. Okay, right, set it to 0. Now we'll go through all the element in the again we'll go through all the element in the frequency and see how many times that max frequency occurs. Okay, so again for each int set int f in frequency, what we will do is simply Take our frequency equal max frequency. If it's equal, we are doing max count is equal to plus plus. Okay? Now what we're going to do is simply go through the formula. So that is int that will be 2. So that will be 1, that is max path. That will be whatever our max frequency is, minus 1, that will be our max frequency minus 1. Okay, int max frequency, and what is the other thing? Sorry, part count, part length. Okay. Part count and part length. So what is the gap? So to get the gap, that will be max count plus 1. Okay, so that way max count plus, sorry, n plus 1 gap. Okay, that will be n plus 1. The same element after. Okay. Now what I'm going to do is simply use the formula int result will be part COD count into part stage length plus whatever our max count. Then what I'm going to do is return max of either whatever our task, that size max, no, mean, sorry, max of this, so we'll get 8 max of, if our task size is greater or result is greater. If our result is greater, we'll return that, or and convert it into int because we are returning int. Then our task size will give us float. Okay, so this works. So before submitting, I think we should copy this, paste it, comment with explanation of, comment with explanation of it. So now this is nice. Paste it, submit it. Okay. Still it is running O of n time complexity. Now it's from the, so what's it called? O R in U apply formula paste APPRO research approach. We got it from the ChatGPT. That's why we did the ChatGPT from the list approach ChatGPT. Okay, now let's move on to the next problem again. So move on to the design tutor. So it's a design problem, so we will leave it at the, it's a design problem. So we'll not do the design problem right now. We'll do all the design problems together. So now again, let's now let's Let's start a timer. Now let's go to the problem and try to understand it. So find the median for the data stream. The median is the middle value in an ordered list task. The median is the median value in ordered list task. If the size of the list is even, there is no middle value, and the median is the mean of two middle value. This we have three. For this we'll have okay. So for odd we'll have median. For even we'll have median 2 plus divided by 2. Okay. So implement the median finders loss. Okay. So this is also a design problem. So leave the design problem for now. Okay. Okay, so we have completed most of the problems from this non-design problem. We will leave the non-design problem for later. So let's see if we can find non-design problem from this one. And this is also a design problem. Reorganize string. Okay, so reorganize string. Okay, so let's see if it's a design problem. So no, it's not a design problem. So let's again, it's a medium level problem. So let's go to the single threaded GPU. Okay, so there are n tasks labeled from 0 to n minus 1 represented by n. There are n tasks labeled from 0 to n minus 1 represented by a 2D integer array task where task I is queue time and processing time. So in queue time, when this will run, how long it will take. So mean that ith task will be available to process in queue time and will process for this much time to finish the processing. You have a single threaded CPU that can process at most one task at a time and will act in the following way. If the CPU is idle and there are no available tasks to process, the CPU will remain idle. If the CPU is idle and there is available task, the CPU will choose the one of the shortest processing time. If multiple tasks have the same sorted processing time, it will process the task with the smallest index. It will choose the task with the smallest index. Okay. So once the task is started, the GPU will process the entire task without stopping, and the GPU can finish the task, then start on instantly. Once the task is started, the GPU will process the entire task without stopping. The GPU can finish the task and then start with a new one again. It's similar to the last problem, but few changes like it process the shortest time and this index. Okay. So we have this. So again, from the last problem, we can think of this like a what do you call it, queue. Okay. So you can think of this like a queue. The event goes as follows. Okay. So at time 1, the task 0 is able to process. So available task 0. Okay. So at time, so also at time 1, the idle, so it will run for 2 seconds. The idle CPU started processing the task 2, available task 0. So at time 2, the task is available for processing, available task 1. At time 3, the task 2 is available for processing. Also at time 3, the GPU finishes the task 0. Okay. Start the processing of task 2. Okay. The task 0 start the processing of task 2 as it is the shortest. It is the shortest available task. Okay. At time 4, the task 3 is available for processing. Available task is 1, 3. 1 and 3. At time 5, GB finishes the task and start processing the task 3 as it is shortest and available. The task is 1. At time 6, the GPU finishes the task 3, 0, 1, 2, 3. Start processing the task. Shortest processing time. So how can we sort this? Like we'll start at time 2, time 1. The task 0 will be available. So what do we do? Available task. Time. So what do you need to do? We need to return how we are going to process this. So at 0 time, we will process this one. At time 1, we'll go through this. So we have no available. At time 1, we'll go through this. If there are tasks available. Okay. So we'll add 0. We'll add this. We'll go through this again. But we can use a heap for this task and time. So whatever the mean is, minimum time. So that is this. How can we do this? Like we can start. We need to create a function with available task. So at task 1, at time 2, we'll go through all this. See what are the available tasks. We'll add it at the available task and perform that task for whatever the time required. And every time. So at time we added this to task. So at time 1, we have just only one task. We added it. We try to process it. So it will take 2 seconds to process. So also at time 1, nothing. Also at time 2, we'll add this one. Task 1 is available to process. Available task is 1, and task 2 has been finished. Okay. At time 2, task 2 has finished. So we pop that one again. From that one again. So let's do this one. How can you do this? 1, 2, 3, 4. This first one is the time it takes. Okay. We see what at what time. So we'll do, let's create a priority queue of these 0, 2, 3, 4 with pair of its index. Okay. Pair of its index. Okay. So what we will do is create a priority of pair of int and int. Okay. With greater int. So we create a mini heap. Okay. So priority queue. Okay. So how we can I add vector? So it's a task dot begin and task dot end. Individually. Let's add each vector int to its task. Still task. Otherwise, so what it is that let's what it is scheme 0. Okay. And index. Okay. So index plus plus. So we have that one. Okay, now what we're gonna do is we're going to start a loop. Time as time passes away. Right. Six the time 6 we have to finish the task 3 0 3 3 0 1 2 3 4. It's negative task time 4. That's inside task 1. It becomes idle. First we add even if it's 1 and 1 2. So 1 starts it. And we have 1. So we have 11 task At time 3, the task 2 is available. At time 2, the task 1 is available. So time 3 will start. So at time will take 2 seconds. In this much iteration, we have these two labels. We have both this. Now on this both which has the less processing time. So this is less processing time. So it process the at time 3 will process the 7 task. The available task 1. So for second task to process, it will take us 2 seconds. So at 3 at time 4 we'll have this what's available. At time 5 it will take 2 seconds. So at time 5 our second task has been finished processing, and we have these two in the and these two in this, so which has less processing time, but we are both available which have less processing time. So one has less processing time, so we will run this one. So we have 1, so 6 times 6, so we have ability to process. We'll start this and then finish it. So while so we need to build available task, we need to create a vector of int as available API task level task. So we have available task 1. So at whatever the top of the element, the time has passed. The time has passed. So at time, that time is like whatever the minimum is, we need to pass that much time at least to get that. So at time 1, so whatever the pk dot top is that first we have this, and pq dot is here in the second, pq dot top this is second. So available task, whatever the top of the stack is, so it will be anything. All the tasks has started on 7. Okay, so this all the tasks has started, so we cannot do this. We need to choose the minimum processing time. So if two are similar, so in this case all of them are similar, we cannot take the top one, that is 7. So if we start this one, it will be started. So what we're going to do is start the time from 0, 1, 2, 3, 4, 5. We keep on going. We'll go to 7. So we'll see which has But instead of doing this, we need to at first iteration, whatever it is, instead of going like this, we'll start at time 0. So what we can do is simply write true. Okay, simply increase the time. Times whatever we did top first, what it is, we'll add all this to the task. In this first we'll add it to the available task. So what we're doing is I it's available tasks dot push back what we as well executed top dot second way. So at that time we have all of these to process. Let's see if instead of if so let's say at 1 second, let's say for this one, we'll put this out 7 seconds. For 7 seconds, we add all of this to available tasks. So we have all these available tasks. If that size is greater than this, if we have available task that is size is greater than 0, we have tasks available. So what we want to do is first what it is, we have all this task. Now once we have available task, we will again loop through all the tasks and find the one with minimum processing. Okay, minimum processing power. Processing. Okay. If the task is greater than 0, if okay, we added all of these to tasks. Now what I'm doing is check which second index. Each task also each int I in will be given variable task. What we do, we have in the index task I so at this index this actually one of it. So we do not get this one, this one. So if we have available tasks, what do we do? Yeah. So yeah, let's check. Now we're gonna do second index. So we do this, we'll take the first one, see if, let's say we have all these available tasks, and now we need to find the minimum one. Let's find the minimum, that is 2. For what element, what I. So how can we do this? Let's say we have this 10, see if we see the processing time is also being slower in this. Processing time will be simply int, okay. Accent. So what do you check? Very simply check that's processing time. So main processor is processing time is smaller than if our this task is smaller than our main processing task, what we do is it this level, what we do is so for this 10, so it will be 0, then this will not happen. This will not, then this will be minimum for this one. So it's minimum is this, minimum processing time. Okay. This is the case, if this is true, so also it's a task I one of it. So now we have this again. Let's put it. I so task dot. So this is greater than 0, then only be this one. For protection, okay. Then only we with this. If there is something to process, we'll process it. Okay? So we'll get a minimum task. So we'll get that. All the tasks. Whatever the minimum task is, we will create. So to vector of need result. Okay? So whatever the minimum processing task is, at the end result push index again, push back index. So we have minimum processing time. So all of these together, push that into this. So first what it is, available from that. We're gonna get the minimum processing. We'll add it to the list. So now we have added 4 to the list. Now available task will be this one. So what you need to do is you need to whatever minimum end of this, you need to pop that. You need to give the task. Release whatever that index. Go through all of this. So we'll go through all of this. Whatever task. Go through all of the tasks. That's nice. Pop that. It is. That's it. Just erase that index and then pop this. So now we'll have updated this task. So minimum processing time. This time. Again, next iteration we'll go ahead. Spare. Execute it. Pop-ups. So we have all this, pop this in next iteration. See if we have while without it's not empty. Okay, it is not empty. Then I'm going to do the same. Go through, get all the available tasks. Get all the available tasks. Erase that available task from this. We add this. We add this in next session. 7 seconds. Because next whatever this second is, we are not 8 on the 8th second. We will still have this one. 8th second and 9th second. So this is 2, 7th is to start 8th and 9th. We are going to process another one. So whatever the minimum processing time is, 2, 8. So now we have minimum processing time. So what we will do is process if it is available for 0.0. Minimum processing. And our minimum processing time available 0, then only this. So that means we have processed whatever has to process. So set it 0 by default. It will be 0. We come here. We add the task. Once we have the task and our minimum processing time is 0, we'll come here and set minimum processing time to 6. So this is the processing will be max int. So now we have processing available max int. Why is typical task? Button process. Get that. So for this iteration, I'll do this, add this, minimum processing is equal to this task. So at the end, let's say we have 2. So let's say we have 2. So at the 7th second, we added that minimum. At that second, we have minimum processing time. Once we have whatever the minimum processing time will be, in processing time minus 1. Sorry. Whatever the mean processing time will be minus 1 second. Once we erase that, add that. This time. So we'll increase the time. So at 7, it will go to 8. And here before processing, because we need to add it the time power. Greater than or smaller than the time that we add the 7. What it is, power. Yeah, this is essential processing time should be, if it is greater than 0, whatever we do. Processing time minus 1 second. So it will come here, go there, for 7th second, for 8th second, it will come here, it will process. For the 9th second, it will be 0. So minimum percent will be 0. So you do not need to do this one. Okay, so it will be 0. Perfect. Please return the result. This will take if the result at size is equal whatever our TDS tasks that size 70. There is a include file you need to include to this one. That is a C limit. So once we add C limit, then we're going to int max, not max it. So int. Is just it here. Okay, remove and from specific element from the vector, whatever it is, replace do not take index, what it takes on iterator. So this 2340. So remove the element at index 2. That is array 30. So we want to specific value. See, sorry. Total. That value not in this one. But then it's a decision. If this works out. So we are getting error. So output is 13 by I think it's not visible for less than equal to. And because of the index, okay, because of that, because of the index issue, we need to be less than or equal to. Okay, we have 2 6 by getting 6 2. So I think if we find the minimum, the next element should be smaller than that one. So if our tasks, let's say there is a 2 tasks with similar value. So, suppose this will continue it after a few. I'm going for a lunch. After lunch, I will continue it again. Okay? So it's So we'll continue the problem that we are doing. Okay. Okay, so what's the issue? Like, we need third, fifth, 5 than 3 because 5 is smaller than 3. If we go to 5, 0, 1, 2, 3, 4, 5, so it has 24. Then 6, 7, 8, 9, 10, 11, 12, 13, it's also have 24. So what you need to do is check if this is smaller than processing speed and I. If it is less than, what do we do this? Okay. And if it's equal, if it's less than, so we'll move on here. So it has 49, it has 11, so it will be added later on. So both are there. So what you're gonna do is whichever indices is less, if both are in the available list. So what you're gonna do is if they are equal, if the processing speed are equal, else if task tags as I and 1 equal mean processing. Okay, minimum processing. What we're gonna do is simply we're gonna check, and if there will check if our current I is less than I in index. If our current I is less than index, then only we'll do this. If it is smaller than, we keep on doing this. If we get equal, we'll check if our current index is smaller than previously. Okay, previously whatever the index we have chosen. Okay, we'll do this. So the music banda copyright like this. So I is less than index minimum processing. So we'll do this. But but still we have one slight issue. First we add this one, then we add this one. We need to do these. Let's say first index. Our index will be whatever the whatever TS task dot price. Okay, index will be this one. Because we need let's say the first iteration. In the first iteration, if we do this, we can get the problem out. That will be issue. Or instead of doing this, we can even do the intermax. Okay, if we want, we can add a intermax here. So for this specific problem, because due to the we are getting time exceeded. Okay. Okay, so we are getting time exceeded problem. Let's put this here. Let's see. It will be single threaded. Let's put 138. Is that correct? Okay. That's correct. Problem, but you have a major efficiency and logical issue. Since this time, this, yeah. So I get that time issue. Like, if it's true, we do this one. Instead of doing this, we need to wait for longer period of time. First we'll come for 1 second, 2 seconds, for 3 seconds, for 4 seconds. What we can do is simply we can do is time is equal to whatever the let top that first time. So we'll start with this. We'll have 1 plus if it is whatever we have added. So once we have a processing element, what we're going to do is we have minimum processing time. So whatever we say, we have 7. Then we have minimum processing time of 2. So we'll directly add 2. So instead of doing this, what we're going to do is what I'm less than equal to say that so once we get the minimum processing time, so we need to extend the time by minimum processing time. Simply what I'm going to do is at the end of this iteration, we have minimum processing. So what I'm going to simply do is extend the time plus equal to min processing, the minimum processing, so that we push it. We'll go here. Our time with this one. So all the elements again we'll go through this one. Still we have time exceeded. So let's leave it to this. Instead of doing this, we will add time whatever time plus in PRO CSS and the processing. And whatever the processing is. Yeah. And plus 1, okay. It does not matter if you do plus 1. Runtime error and time equal to time plus processing plus 1. So time is equal to 0 plus 1, that is 1 second. So for this, for the first task of this, that is to be minimum time is so for this we need to minimum processing time first one. For the first one, our minimum processing time is everything will keep is equal to 0. I do not need to do this. Okay. Not care about if this is 0 or not. We do not care about this. We get whatever the minimum processing time is. We're going to add that so that let's say we have 2 seconds, so that will be 7, 8, 9. So 9. So we'll add 9. So at the 9 second, whatever that is, we added. Now the starting time will be time plus equal to mean PRO CSS processing. Okay, so minimum processing. By default it will be 0, so 0 plus 0, so this would never run, but instead what we're going to do is whatever the top, that is mean, the minimum time, so we need to go up to the minimum time, so we'll directly put the 7th second or whatever the second. For that what I will do is top the first. Okay, so what's the issue? We are getting integer out, so instead of integer this should be time should be long. Okay, okay, let's add this to over here. Let's run it again. And once we add this to, okay, still we are getting time exceeded. Okay, okay, we are adding it, and we are going to all the elements, and we are going through all the available, checking which is the minimum one. So we still we are getting the time exceeded. So what I think there is a instead of going through all the tasks, we should have another priority queue with instead of processing time and index. Okay, so processing time, minimum processing time, is a minimum processing time, and what's its index. So once we come here, if our size is greater than 0, if our available task is greater than 0, what we're going to do is from the available task, we're adding available task, and it's this will also priority queue. Let's make it also priority queue similar to this one. Okay, let's make this also priority queue. Okay, with minimum priority queue. Okay, so this is also minimum priority. This is also priority queue with what do you call available task, and so what we are going to push our what do you call first as a second, whatever the top index, so that index second value. So what we're going to do is TSD task pq dot top dot cc 0 and second value, that will give us the first index, that is 1. That will be our what you call sequence. This will be our priority queue on what we are going to see. So once we have created that priority queue, first index as first is this one, and second is there's no label, so so they will put us need to put this into curly braces. So this is the second is the index. The first one is the whatever the index we are on, second element, and then we are sorting it based on this. Then what we will do, once we have available, if our available is not empty, so what we will do is, if our API available task is not empty, if our available task is not empty, what we will do is get the top minimum element. So now we have all the available tasks. This. Second is the index. Now instead of going through all the index and processing, finding the smallest processing speed, we can have just smallest processing speed by doing the what do you call it? The top now. Simply our mean PROCSS and the processing will be ABI task dot top dot first again. So that will be give the top. Insert a push back, that will be PAI task laptop second again. Now we have minimum processing. We have pushed that we get the minimum. We added it to this one. Instead of doing all of these, get the index like I will have both. Okay. That will be the interesting issue here. What if the second is also available as so we are getting 0033. So we're doing it based on processing speed, another index. So whatever has the minimum processing in this one, we'll add that to the let's close this one. We have added all the tasks. Just from all the added tasks, if it is not empty, whatever the top minimum time taken by the task is, We get that one. We get its second index. So for the first, then after getting that, we need to pop the first action. AVAI task tab, pop that task. So we pop that task. So this over here. I think now this should work. I was still thinking like there should be an error. So 201, we're getting on 210 for some reason. I think it's because of these two are similar. So 0, 2 is run first for 3 seconds, then 9 seconds on, sorry, for first this will run, then 3, then 4, 5, then 6, then this will run at 6 seconds. So we're at 1 plus 3, that is 4 seconds. At 4 seconds, nothing will happen. At 4 seconds, nothing will happen. We'll get here. We have added minimum, that is 0. We go to the first smallest one, that is 1. So one element will be added. 1. We will get the top, that will be 3. 3, then whatever the previous was 1 plus 3, that will be 4 seconds. On the 4 seconds, nothing will be added. On the 4 seconds, nothing will be added. So don't 4 seconds, nothing will be added. On 5th, then what will this will go on infinite loop, but it's not going on infinite loop for some reason. So I'll have greater than I go to this. It is empty because we pop it. Now we do this, we pop it, so there is nothing on this one. Let's check this one. We come here, then our time is 1 second. 1 second plus 3 seconds, that is 4 seconds. So is there cube 4 seconds? So there is no 4 seconds. Instead of doing this, time is equal to whatever this plus so first so we have 3 plus 0, that we will add this one. We have to remove this one, so we have 6. So on the second iteration, we have 6 plus 1. Sorry, 1 plus 6 plus 3. So we have moved 1 plus 3 plus 6 second highest. Sorry, long. So this should be set to 0. No. So both will be added. So basically what is happening, I don't know, like first we have 1, whatever plus whatever the top plus 0, we have added 1 available task. So we have added this to available task. We go if available task is not empty, go get the top one, second one, We can do this while here also, like if our not empty, and no, that's fine. Let's be with 0 1, so 1 0 itself. If we go through the task, so now what's the issue? Plus one, nothing happened. 5%. The issue here, copy this, let's paste it. Fix the time problem. Correct and clean version. What's the issue with my code? So at the very first situation, time is 0, the time does not advance correctly. Also, time will advance to the task started task start time if GPU is idle. It's also heap order, so appropriately processing resources could make sure that the task is processing the visual blood is selects what you are currently you already does the because of prayer and processing data. After popping the level task, you set but then immediately add the time in the next loop. This works but can be simplified by just adding the task processing plus time in the loop. Okay, so we can do this. Do this. Let's go to this side. So we do not need this side. We do not need this if there is nothing, so then we will add time plus possible. So that this works. Now this works because okay, now we're able to complete the solution, but so this is more of a cleaner solution, but I'm able to like at least solve this problem. Okay, it's taking a lot of time, but I'm able to at least solve the problem. Okay? So instead of doing this, we can copy this. Sorry, got it. Paste it here. While this is not equal to this, and I'll do that again. Yeah. again we are getting time exceeded. Well, size is not able to. Okay, so now in next video, I think next session we'll still go through this. We'll go through this same problem. Okay, we'll go through this problem again. Okay, we'll go through this problem again, but by watching this video and trying to solve according to this. Okay, so for currently this is it. Then in a half an hour we are going to continue. I'm starting a new series, and since I'm trying to do OpenGL, I'm trying to create an OpenGL project live. Okay, so what I'm basically doing is creating a physics engine for using OpenGL by myself, but I have already learned few of OpenGL concepts, and based on that we will learn and do the OpenGL project